Okay, what's up, y'all? Dude. All right. Big class today. Big class. We think more folks are coming? Over under? 3 or 4? So you have a over under on 6.
Under 6.
Under 6?
Over.
Oh my god. Over 6?
I'm optimistic.
Optimism. All right. Oh, that's the wrong class. You're not modeling chaos. Okay. So that was spring break. We did initial value problems. I still don't have a name here. But we're gonna finish up those initial value problems. So we'll just briefly talk about what we talked about before, for folks who didn't make it, or maybe weren't there for the end of that discussion. And then, like an hour in, we'll sort of switch topics and we'll do our normal class. We'll do like a 30-minute presentation about simultaneous linear equations and eigenvalues. And we'll try and do the homework for this week. So we were working on 9.5, and let's just bring us back to what that meant. We were solving these two forward time-centered space equations, okay, for the wave. So we had a wave on a string, and on the right-hand side, we are just updating these values. So you had phi and psi, and these were arrays. So to get your new phi prime, it's just the old phi plus h, which was small, times whatever the velocity was, essentially. And similarly, we had something like psi prime, which is phi, or sorry, psi, the original psi, plus some information about the curvature of that location. So this was solving the double differential of time on the left-hand side by breaking a second order differential equation into two coupled first order differential equations, right? And then on the right-hand side, it was a double space derivative, and that's just captured here by the fact that if I move left and right in the middle, I get an approximation to the curvature. Okay. Conceptually, is this making sense? Okay. I was hoping that, some folks would be here, but if necessary, we'll just pair up with the two teams that we have here working on the code that we had. Should I go run down the hall and scream at people? Are there people in that room? I know that some folks are focusing on the modern physics exam.
That's right.
How's that possible? Can't be in 2 classes at once. Maybe it's a different exam. Is modern physics right now? Oh, maybe it's a different class I'm thinking of. Solid state exam. Okay. Okay, so maybe people are focusing on that instead of wave equations. I don't love wave equations. Okay, so let's pull the code back out and let's remember how we're doing this. We want to start with an equation that looks like that. That's what our velocity is going to look like. And it's going to devolve into this as we increase h. So we intend to break the computer, right? Okay. Here's the problem that we're going to talk about today. Some folks, I think, are struggling with how to set this up. So let's just do a quick reminder for how we're going to address this. In the previous problem, when we were doing we were doing diffusion, and we had temperature updated and temperature now. And so we would update the temperature based on the current temperatures, and then we would swap them. So we had one array that had the new temperatures and one that had the old temperatures. So in order to do that, we start by creating all the arrays. So you have all these arrays, and you give them all some initial values. Then you have all the updated arrays, and you give them all some initial values. And then you let it run. Okay. So we're going to do the same thing here, but now we're going to have 4 arrays instead of 2. So we have phi and phi prime. We have psi and psi prime. So we need to initialize all of those values. Okay. How do we initialize phi and phi prime? According to the text.
So there's 0, right?
There's 0 at the beginning, right? And so when I write something like phi of x equals 0, what I'm really trying to say here is that not only phi, but also t equals 0, right? Because phi is a function of both t and x. Okay, so we initialize that. And what about psi of x at t equals 0? We have an equation. Good, so the best way to do that, best way to initialize that function is to
Unless it's a 5 function.
no.
No.
No, you could do it that way, but it's not necessary because you're only going to call it once. You're never going to use it ever again. All right, let's have a look at that. So that says C x L minus x over L squared exponential. And this is all inside of the exponential. That's going to be minus x minus d quantity squared all over 2 sigma, right? Okay. So what is d here? D is some location. L is the length. So if we have this picture of a string like this, great picture of a string, right? Then this is L, right? And if you recall, we cut up the entire width of whatever we're looking at. We slice it into pieces so that we can fit it inside these arrays, right? So we had something like all of these little markings like that, right? So we have L here. Let's scroll back up if we can. Here we go. Here's L. Here's the number of divisions. Look at that word, grid spacing. Okay, so what does that mean? Grid spacing.
How far apart each division is?
Good. So if I look at this equation here and I say x, how do I relate x to what's inside of my array spacing?
It can only be integer values in the array spacing.
Right, yeah, so it has to be integer values of the array spacing, very good. And what units does x have here? It has to be a length, right? Because it's length divided by length squared, or length times this thing is a length. So it's length squared over length squared. Now this thing I know is whatever 1 meter or something from the original. But how do I write x? Well, x needs to be equal to a length. Good. Does the index have a length? No. So the index is always like I or j, however you described it. But now I need to multiply it by something. What would I multiply it by? A, the grid spacing. Good. So that's what I'm going to do. So anytime that I see x in here, I'm going to replace it with I times a. Now, of course, those are going to be times, not IA as a constant, right? And then all I have to do to initialize this is simply take a little for loop. So for I in range, and I forget how it's done here, but if you scroll down, it says right there, okay, 1 through n, right? And then I can just walk along through psi, and I can write that in. And I only have to set it once, because everything we do afterwards is going to update naturally. Does that make sense? Okay. All right, that's 6. We're close. We're close. Does this process make sense? No? It does? Raise your hand if it still doesn't make sense. Isaac, I know you're left out from the last one, so we'll work on that together. How you doing? How you doing? How you doing? You ready? Okay. All right. So let's code this one up. Let's finish this one. I'm hoping we'll get through it before 2, and that'll give us enough time to switch over to simultaneous solutions, and then we can go from there. Does that work? Okay. Let me pause the recording instead of stopping it. Okay. And we're going to sort of switch gears to finish up the discussion of initial value problems. One thing that, Gonzalo kind of alluded to is, okay, how do I make it better, right? How do I get it not to fucking break? And that would be to use a different technique. So here you have something called the implicit method, which would be to use information similar to the way that we did it before with RK4, which would be to change the way that we take steps forward in time so that we update the data appropriately, so that the numerical instability doesn't develop. And so therefore you don't run into something that is non-physical, right? So you have different techniques. This is called the implicit or the Crank-Nicholson methods. If you go through this, you'll also find that there's a technique called the spectral method, where you, instead of doing a finite difference, you do a finite element. And what that means is a finite difference is the way that we took the derivatives beforehand, but you could write this as a series of sums. So what I mean by that is you create a Taylor expansion or a form of an expansion here, and you transform it into the combination of sinusoidal curves with varying amplitudes, right? And you can do this for this type of problem because it's fixed at the ends, so therefore you know that it's periodic, right? And that would be a perfectly good way to solve this problem. So when you look at the further exercises, and potentially this might be part of your homework, you may notice that there are different techniques for doing different problems. And so I would encourage you to read through some of these different techniques if they're interesting to you for your specific final project. You might find that you have a differential equation that can't simply be solved by RK4. Or, if you have something that on one hand side solves the Laplace equation, and on the other hand solves a double derivative in time, right? That is something that might need a different type of technique. Does that make sense? Okay. Yeah, these are all the different types of problems that can be solved with these derivatives. Wave functions, Schrodinger equations, so that's quantum mechanics. Even when you get down to, I guess that's random processes. So if you look in the end, I think of chapter 8, they talk more about the ODEs that can be solved. So that includes stuff like comets, orbits, stuff like that. And there's additional techniques in the end of that one too, that talk about how you can use different types of techniques like the Verloop method, which changes how you do the time stepping so that you conserve angular momentum, or so that you conserve energy. So there's always different choices you can make in your approximation such that you have conserved quantities. If you remember when we did that orbit, and we had an orbit going around, and it would get smaller and smaller and smaller and smaller until it fell into the thing and then it kicked itself out. So what was happening there is energy wasn't being conserved. Because of course, if the energy in the simulation is conserved, then there's no way for it to get smaller. You may find that if you use a specific type of algorithm that conserves energy, it may start with some elliptical orbit like this, but angular momentum won't be conserved. And you'll watch for 10,000 years, and all of a sudden you'll notice that it's the same size as it was, but now it's oriented differently. So there's always trade-offs that you have to make when you're computing something numerically. And if you go into grad school, if you go into any sort of professional industry that uses numerical modeling, you'll learn the ins and outs of that specific type of model. Does that make sense? Okay. Questions, comments, concerns? Okay. That's it? You ready? All right, we're gonna change entirely everything. Look at that. New chapter. Simultaneous linear equations. Ugh. That sounds like math, Mateo. I hate math. Okay, computer does math for us, so we're really excited. So let's go back up to chapter 6. Oh God. I guess it's like really far up here. Fourier transforms. If you like Fourier transforms, we can go back to that at the end of the semester. But normally you can just find a pre-programmed fast Fourier transform. Okay. How do we feel about our linear algebra classes? You took it recently, you're like, love it. What? 3 years ago? All right, here's what we're gonna do. We're gonna take the brush and we're gonna get rid of all the cobwebs, right? And then we're just gonna remember just enough to be able to code it. And then we're immediately gonna forget it all again, because that will allow the computer to do the solutions for us. Okay. So we're gonna talk about solutions to linear and nonlinear equations. So here's an example of simultaneous linear equations. So what do those words mean in that order?
Or, linear equations, there are some linears that are only either multiplying or adding. And, we have 4 unknowns and we have 4 equations.
Okay, I'm gonna agree with almost everything you say there. I just want to ask one qualifier. Is that linear? Not linear. Is this linear? Why is that linear, Eduardo? I just know it is. Linearity talks about linearity with respect to what?
Just because it's not exponential.
What do you mean exponentials? You mean powers?
Yeah.
Powers. My powers are different from exponentials here. There's nothing in the exponent, which is correct. But exponential, I think of as e to the x. Right, yeah, so y squared. So there's no powers of x, y, or z. Right? But similarly, I could divide both sides by y. And this would be 3x equals 2 over y. Is that linear? No? Why not? Because there's an exponent. Right? That's how we can write 1/overs. That makes sense or no? Okay. Is that okay? Okay. So here I see, just like Alfred was saying, they're all, none of them have an exponent. Okay. That's the linear part. What's the equation part? We have the equal signs. Okay. All right, very good. What about this one? Exactly, right? So it's not as though I wrote down 4 different statements that have nothing to do with one another. This one tells us about this one, tells us about this one, tells us about that one. Right? Okay. If I take that, let's write these relationships down. 2w plus x plus 4y plus z equals -4. 3w plus 4x minus y minus z equals w minus 4x plus y plus 5z equals 9. 2w minus 2x plus y plus 3z equals 7. All right. Is it possible to know what w, x, y, and z would be to make these all true? It is. Is it? Some of you say yes. Some of you are on the fence. Okay. How would you do it? What's that? Substitution. So what would you do? You don't actually have to do it. Just tell me what you would do.
We would we equal to one variable, and then we can use that variable to plug in into the next equation. And then we would continuously do that until we run out of 4 variables, and everything would take like 1 variable.
Okay, so I could take this one, W, and I could take all that stuff, I put it on that side, and then I'd put this W into all 3 of these. And then I'd solve this one for Y, and then I put that into these 2. And then I solve this one for Z, and I put that into there. And then I have to go back and I have to unsolve them all, right? Is that the most efficient way to do it? Takes forever. Correct. It takes forever. Okay, that's what I want us to identify. Okay, so humans are slow. That's what it says right here in the textbook. So it must be true. This is published. And they're prone to error. Have you ever made an error while doing this? Yeah, many times, right? Okay. Okay, so let's think about how we can write this in a different way. Here's how I would write it if it were a matrix. We like matrices? Matrix our friend? Okay. That's a good point, but that's not what I mean. So let's just think about how matrix multiplication works here. Let's remember how we take this row and we multiply it into this column, and you get the first element. We take the second row, we multiply it into the column, we get the second element. So this is what type of a matrix? Square, and what's the size? 4 by 4, correct? With 4 elements by 4 elements. And what's this one? 4 by 1. And this one? Yeah. So how do we know what the elements will be at the edge? We look at the outside. So we have 4 by 4, 4 by 1. So then multiply 4 and 1, and the one that we grab on the side. This is 4. If I multiply this on this side, what would I get? Do whatever I want. It's just math. You get a 4 by 4. That's correct. Good. All right. So yeah, so that's the only tricky thing that you want to make sure that you don't do, right? Don't accidentally multiply elements in the wrong order, because matrix multiplication, unlike the rest of multiplication, is not commutative, right? So A times B is not equal to B times A necessarily. Okay? Okay, so we can write this out shorthand. I have A. I have X. X is my vector here, and V is my answer. Right? Okay, so how do I find the solution for A? So this claims that one of the ways to find the solutions is to find the inverse of the matrix A and multiply both sides of it to get the solution X equals V inverse 1, A inverse 1V. Okay, what does it mean to take the inverse of a matrix? There's a formula for it. Okay, good. That's the way we want to think about everything in our lives. What does it mean, inverse? Row and column would be transpose, right? So I could have something like A transpose would be to switch rows and columns. Okay? What does a to the power minus 1 mean?
It's 1 over.
Hey, whoa, wait, whoa, wait, whoa. I just mean, what does it mean in English?
Reciprocal.
It's the reciprocal, right? So a minus 1 is the inverse. And what happens when I multiply a minus 1 times a? Yeah, you get 1. And because it's a matrix, you get what's called the identity matrix. Okay. What's the identity matrix? All right, now we're all warmed up. Now we're all ready to fucking, all right. Okay. So let's see if we can do it. I want to create a code that allows me to take the inverse of a matrix. And the first thing that we'll do is something called Gaussian elimination. Why is it called Gaussian elimination? Because a dude named Gauss made it. Okay. You may say to yourself, man, there's a lot of stuff named after guys named Gauss. There's a lot of very productive mathematicians named Gauss, and they're all related to each other. Just like a whole line of great mathematicians. And now everything is confusingly called Gaussian. Okay. So the first one here is you have some rules. This is the rules in order to solve the simultaneous set of equations. So this one says you can multiply any of the equations by a constant and it's still the same equation. So this one here, if I multiply by 2, I have to multiply each term by 2, right? And the solution is the same. You multiply it on both sides. You also know that you can take any linear combinations. So I can add this one to this one or subtract this one from this one, right? And that's okay too. Okay. Similarly, you can use these operations to solve this. The first thing we want to do is we want to reduce each line by line, okay? So the first thing we're going to do is we're going to take the coefficient here and we'll divide the entire row by it. You see that happens? The first one is 2, so we divide every term by 2. So this is divided by 2. This becomes a half. This becomes 2. This becomes a half, and this becomes minus 2. And you can see that right here. That's the first step. Right? Okay, now what? On to the next row. So note that the first element in the second row of the matrix is a 3. If you subtract 3 times the first row from the second element, it'll become 0. That seems reasonable, right? So I'm going to take this row here, which now has a 1 in it. I'm going to multiply by 3 and subtract it from this one. So the 3 W's cancel. Right? And you'll see why I'm doing this in about 2 seconds. Okay, I'm not going to go through the rest of the math there, but you can trust me or trust the book that they did it right. So I got a 1 in the top. I got a 0 in the first column. Okay. Now let's do it with the third and fourth rows. And look what I'm trying to do. I got 1 and I got zeros all the way down. Okay. So now I've eliminated all of the W's except for this one at the top. Right? Okay. So let's do it again. Let's move to the second row of the matrix and perform a similar series of operations. You divide the second row by its second element, right? So it was 2.5. Now we divide this whole thing through by 2.5. And I get a 1 there. So what am I going to try and get here? Zeros, right? So now I have 1, 1, and then the zeros. And then I'm going to keep doing it all the way down. So you'll notice in the bottom triangle, I got zeros here and 1s here. And all of a sudden, it's clear, right? What's Z? 1, it has to be, right? Because it's this thing here times this thing here. So Z has to be 1. Simultaneously, you do happen to get Y here, but not necessarily because this would have a coefficient in some cases. But now you can back substitute, right? Okay. Well, now speaking of back substitution. So here's how we define the different elements here. This would be called the diagonal. You're familiar with that? That's along the diagonal. What's the bottom called? This bottom thing? Lower triangular. Good. And what's this top thing called? Good. Now we're totally we're experts at linear algebra. Okay. So let's do back substitution. Generally, we might have a form that looks like that. Gaussian elimination gives us the lower triangle, lower triangular as all zeros, so that we can do back substitution and get the solution. And it just looks like that, right? That is what the triangle looks like. First coefficient here, z equals 1. That's what we just learned. And then you have to put that one back in here in order to solve what z equals 2 is, right? So you would move this one over, so on and so forth, right? And there they are. They're not complicated. Okay. So let's work an example. I hate examples. I hate computer. Okay. So let's create this array together. You're going to create a vector, right? And we're going to do Gaussian elimination. Does that make sense? Okay. Each one of you should have your own sheet for this. Okay. And if we want to go back over that, that's perfectly okay. And then we'll just do this circuit of resistors problem, and then we'll be done for the day. Is that reasonable? I think it's this one, 6.1. Yeah, let's go. Let's go. Okay. All right, so let's continue. And you learned how to do Gaussian elimination and back substitution. So now we'll talk about pivoting. Like friends. Another one. Pivot. Oh, fucking all right, whatever. I'll just kill myself. So let's suppose we want to solve slightly different equations. So what happened here that's different from the last one? You have a 0 on the diagonal. Very good. Okay. So just one thing changed. The first row is 0 where previously it was non-zero. This makes a big difference, right? Because if this is a 0 in your matrix, what does that mean? Can I ever multiply by this and subtract it from this to get rid of it? No, right? So that's garbage. Okay, so you're screwed, right? Forever. And nothing will ever get better. No, why not? Zuri's got all the answers today. What you got? Yeah, you just manipulate it, right? You're just like, well, fuck that. All right, let's just do that. Right? I can switch W and X. No one's going to cry about it as long as I switch these two. Okay, good. Done. But you have to make sure that you don't introduce a problem somewhere else, right? So you can do partial pivoting. You can modify this program to include a pivot if you want. It's not that hard to do. So let's talk about a general way to do partial pivoting, which would be LU decomposition. L means what here? L would be lower. U would be upper. Real tricky, okay? So this is a lower upper decomposition, okay? So what's going to happen is we're going to solve it. Let's have a look at a matrix of this form. This is still our 4x4 that we loved before. And we're going to be able to generalize this to as big as we want or as small as we want. In fact, we're going to use some of these techniques. You have a linear algebra solver that you use maybe for a specific type of final project that you might want to do. So to perform the Gaussian elimination, you reduce it to an upper triangular form, right? You can write the elimination process in a slightly different manner using matrix notation, right? So this is how it was before, but now this is the inverse of this one. Okay. So you might not trust this, but this is what this gives. And what you see here is this is the transpose, and this is divided by that first one. This is the first one, right? So if you do the matrix multiplication out, this one times this one gives you A0, 0, and then you divide by A0, 0, and it gives you what? Bada bing, bada boom, right? So we're all happy with that. And similarly, if I do this one times this one, then I'm going to get this element, which is a 0, and 0 divided by anything is, of course, still 0. Okay. All right, so we can go through that whole thing, and you can find that this L0 matrix, which is the lower matrix, is this thing on the left-hand side. Okay? Okay. You can keep going through this process to get each one of them. So you'll notice now that this second one, this L1, is your B11. This is your one element. And now your lower triangular is just this bottom part here. Okay. We don't really need to dig in super deep into these. You can see that they're generalizable. The largest one is the L0, and they get smaller depending on how large or small your matrix is, right? And so similarly, there's L2 and L3. Okay. And so really what you do is you multiply L3 by L2 by L1 by L0 by A in order to get the vector that you wanted, right? So if you have X like that, you could, of course, just multiply it like this, and that would still be true. Okay. All right. Here's your L as a whole. That'll be the inverse way of describing it. Here's your upper. That's the way that you ended up with that matrix. Remember, they were all on the diagonal in the top, right? So we call that the upper, and this would be the lower. And L times U is just A, because that's how we constructed it, right? So similarly, you could say something like L times U multiplied by X would be the V that you had before. If we go all the way down here, we see that L is these values from each of those individual ones that we had before. So this is the LU decomposition of the matrix A. And each one of these D33 or C22 or B11, they all have a very specific format that's a function of whatever the original values were. Okay. So let's go ahead and go all the way down here. Yeah, it's okay. So from numpy dot lin alg import solve. That's nice. That's really nice. Okay. What does solve mean? Well, solve is going to do a lower upper decomposition and back substitution such that the stuff that you just did is not necessary. Okay, so you did it in order to get the skills. And from now on, we're going to let the computer do all of it for you. Because what did we say earlier about linear algebra? It's well, that's one way of thinking about it. I think I said that it takes a long time and you're prone to human error, right? You're prone to fucking up, right? So let's not do that. And generally speaking, when we do anything in this class, the first time that you do it, it makes sense to do it by hand. But if there is a routine that does it, there's a reason why we don't calculate square roots by hand anymore, right? We just put that in the calculator and we say, we trust that you got the right square root. So linear algebra is really going to act a lot like a computer. You have some matrices, you're going to be able to apply things like solve in order to do them. And that will allow us to sort of take a step beyond what you normally would be able to do just by hand. Because now we can use linear algebra to solve much more complicated problems, including how we do integrals, which we haven't even gotten to yet, in a very sophisticated manner. Does that make sense? Okay. So that's LU decomposition. We're going to skip past this problem. Here's another complicated problem. You have the inverse of a matrix. That will be right here. Very tricky, right? NumPy dot lin alg import inverse. Boom, got it. Okay. You may find that you have special solutions that are called tri-diagonals, where they're like 3 across this way along the diagonal. Okay. You don't need the entire Gaussian elimination procedure to solve them because they're almost partially solved, right? These are all zeros down here. So you may find, let's see, where is it? Here it is. Lin alg is slower than this Thomas algorithm, but you could code that up if you wanted to. Generally speaking, we won't be doing it very fast. So let's talk about this one, because this one might be relevant to what folks are doing for their final project. Let's say you have a structure and you have identical masses in a row joined by identical linear springs. What would that be similar to, say, physically? Any physical system this could represent other than just springs? What? A crystal. Why is that? Because if you have, say, a bunch of sodium atoms all in a row, and this one here is the nearest neighbor, it pushes on this one, and this one, not going to like being close to this one, moves towards this one, but it bumps into its friend over here, so maybe it pushes back, right? So you might think of, for example, any sort of any sort of structure, physical structure that's in the solid form could be represented roughly by springs. Okay. This is the basis of stuff like phonics, right? Where you have like sound waves through crystals. Because metal will act like, or metal, I'm saying metals, but what I mean is solids. Solids will transmit vibrations through them, right? Okay. So let's look at the mass times the acceleration. So this is psi, which is just the difference between nearest neighbors. And that's pretty straightforward. So here you have k, and this is essentially x, but it's x of the neighbor to the right. So let's take this guy here. This would be x to the right. And then this one is x to the left. Okay. And then I have some external force, Fi. Maybe I'm shaking the edge of the crystal structure. Okay. And so now what I end up having is I have a whole bunch of force equations. I have one for each of the individual ones in the middle. 1, 2, 3, as many as I want. And I have one on each of the ends that are unique, right? Okay. I can make them all oscillate. So I could say, you know, let's vibrate each of these springs and we'll see what we get out of it. That'll be xi, some initial perturbation, times a time varying. Do you guys, you like this form, e to the I omega t? You know what that means? No? Okay, e to the I omega t is a very special way of writing this because really it's a combination of sines and cosines using Euler's equation. So what is Euler's equation?
Cosine t plus I sine t.
Okay. So this is just a different way to write any set of sinusoidal grouping. And physically, we tend to ignore the imaginary part, but there is important implications for that imaginary part when you want to do stuff like analyze how waves disperse in a medium, for example. Okay. Okay, so we could work that back through and, you know, you take a couple derivatives of this thing. What do you get out if you take a derivative here with respect to t?
Times that,
Times what?
times the same.
And also an I, right? Good. So you get an I omega out. And if you take two derivatives, what do you get? Which is -1 and n omega squared. So now we go back to those equations and we see, oh, there's this nice relationship here between minus m omega squared, which was the first one, x, and that other stuff that we wanted before. And so now we have some information in the matrix form. So we're not going to solve this in terms of like finding where every position is as a function of time, but we might want to know what are the normal modes. What I mean by that is if you let it, give it some perturbation, how is it going to respond as a function of those frequencies, those driving frequencies, right? So you have this matrix form, and you can go through this process here. Here's the constants, here's the initial arrays. You set them all up. So you go through an entire array with as many objects as you want. I think they said 26 different objects. And you do your Gaussian elimination and the back substitution in order to find the dots and the lines. Does that make sense? And let's see if there's a picture. Here's the picture. Oh yeah, there we go. Makes sense? This is the amplitude of the masses within the chain. This is how each one of them moves. So like this one here moves a lot. This one doesn't move very much. This one doesn't move very much. This one doesn't move. Some of them are moving a lot, right? You have 26 in a row. Some of them are moving a lot. Some of them in the middle are moving a lot. And some of them near the normal modes are not moving at all. So you can imagine for a certain frequency, modes are set up and some atoms are excited more than others. Does that make sense? And this is all just using Gaussian elimination and back substitution. So this is an example of how you can solve a very complex system with a lot of parameters. And you may have seen this before, right? We had this example of where we were like driving multiple atoms. Like, man, how do I keep track of all of them? Well, you could do that with something like a coupling of RK4 with a matrix that you keep solving, right? Okay. Okay, now we're running out of time. Let's see if we can get to what I want to get to. Eigenvalues and eigenvectors. Are you familiar with this? Okay, what does it mean?
Everybody was a solution to the only states that exist naturally.
Okay, there's another way to say that. I do like that. That's a good explanation. There's another way to say it that that takes into account like how would I explain this to someone who doesn't know about matrices? Does that question make sense? Kind of. So you're right in thinking about they're in like natural states to some physical system. But let's say I don't have a physical system. How would I interpret something like an eigen or an eigenvector?
It's the only solutions that are invariant under the
Okay, that's even higher. That's even okay. I'm just gonna say, let's imagine some matrix A, any matrix A. Eigenvalues and eigenvectors are just a special case where if I take A and I multiply it by the eigenvector V, I get a constant times that eigenvector V. And the eigenvalues are those constants. Do you see? So this here is a matrix times a vector equals a constant times a vector. That's really what I'm trying to get at. So every matrix has a specific set of eigenvector, one eigenvector, and one eigenvalue, right? And you're talking about, well, the physical interpretation of that, that's the natural mode. That's absolutely correct. That's how you would create this like natural system. You know, sometimes you talk about it in terms of resonance, or you talk about it quantum mechanically as being like the energy. Here, we're just going to think about it only in terms of the math. And the math here says there exists some vector where I multiply that vector by the matrix, or I should say that differently. I multiply the matrix by the vector, and I get back a constant times the vector. Does that make sense? Okay. There's lots of reasons why you'll need to know this. As Alfred alluded to. But let's figure out how to do it. Because once we can get the computers to do it for us, then we can forget how to do it, right? Okay. You could do a couple different decompositions here, but let's just go to, oh God. All right, here we go. So an n by n starting matrix A has the following algorithm. You create the matrix V to hold the eigenvectors and initially set it equal to the identity matrix. Okay. Then you choose a target accuracy for the off-diagonal elements of the eigenvalue matrix. Why am I doing this? Well, initially, this value V, right, it needs to be diagonal because it needs to be a vector, right? And you can calculate the QR decomposition, A equals QR. Then you update A, and then you do it again, R times Q. And then you multiply by V on the right, and you check the off-diagonal elements. If they're all less than epsilon, you're done. Otherwise, they're not. Okay. So this algorithm is short and simple to describe, but it's not easy to do. Okay. It can be done in a few lines in Python. So that's the important part. Let's look at this here. Okay. Here's using the QR algorithm. You import the word array. Good. Linear algebra, you import this thing. Egg. That's eig. H. Okay. So here's your arrays. And here's X and V. Okay. And this is finding the eigenvectors of A. Boom. Bada bing, bada boom. So here's your eigenvector, eigenvalues are X, and your eigenvector is V. Boom. Don't learn anything about how it's done. Just done. Right? And now you have your eigenvalues and your eigenvectors. Okay. Do you want to learn how to calculate eigenvectors and eigenvalues? Do you remember how to do that? Have you ever heard of that before in your whole life? Okay. We definitely don't have enough time to do it today, but maybe at the beginning of Monday's class, we can just show conceptually even how to do it with a 2D eigenvalue, eigenvector, right? Okay. It's fairly straightforward, with a 2x2 matrix. You just subtract the eigenvalues and move it. Let's just really quickly look at, I think I wanted you to do 6, 9. Yeah, 6, 9. See if this can be done or started even. All right. Yes, let's go. Quantum mechanics. Okay. So this problem will also start on Monday. Quantum mechanics is all about the matrices. Fucking love some matrices. Okay. And you can usually solve some very complicated systems as long as you're careful with how you treat the quantum mechanical situation. So let's say here you have a particle in a well, but instead of a flat bottom, you have some weird bottom. Okay. So you still have an infinite well that goes all the way up, right? So the particle can only exist between 0 and L, but the potential at the bottom is not flat. Okay. You can't solve this analytically. You just can't. But we don't care. We have computer. Okay. So here's your Schrodinger equation. Have people seen the Schrodinger equation before? Okay. So what this essentially says, and let me just show you here that this is actually a matrix equation. And specifically, it's an eigenvalue equation. So this says H is a matrix such that when I apply it to psi, which is the vector, I get back E, which is the energy, times the vector I started with. Okay. And here's how we write the Hamiltonian operator. This is also a matrix. So this thing here is essentially what we think of as the acceleration, d squared dx squared. plus the potential. So this is a statement about total energy consumption, total energy present, right? So if this is asking about the kinetic energy and the potential energy, and then on the right-hand side, it of course says the total energy. Does that make sense? I lose anyone? Kind of shaky? Maybe not the right time to introduce quantum mechanics, but let's have a look here. Here's the problem, right? So the wave function can be expressed as a Fourier sine series. So what I mean by that is that you have some function and that can be broken up into the components where you're just adding a bunch of sines and cosines. And similar to how we think about this when we think about a Taylor series, which can be added as a bunch of powers of x. Here, I can simply add up because I know that it has to go to 0 at both ends. Even though it's not periodic outside of the walls, I can evaluate it between 0 and L. And I can start off by saying, okay, the first mode goes like this, right? That's sine. But if I change this little piece here, n, to 2, now it'll do this, right? And if I add this to this, then this comes down a little bit and this gets taller. So by changing all of the different modes in here and changing the amplitude of each mode, I can make any shape that I want inside of something that goes from 0 to 0. This is the benefit of a Fourier sine series. You can also do it with cosine, but then it has to start at 1. That's not what we want. Okay? All right. And these are the coefficients. So for the work that we'll do, and we'll recap all of this on Monday, but essentially you can show that the Schrodinger equation, when you apply this here into here, you take those derivatives, blah, 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 you're going to get out this thing. And each of the matrix elements, HMN, has this integral form. Okay? So you can find all of these H elements, HMN, and then you can find the eigen values, which tell you for some arbitrary shape bottom, right? Whatever the bottom is that you want to pick out, you can get whatever the value for the energy, base energy, the first excited energy, the second excited energy, so on and so forth. And that'll tell you about the eigenvector itself, which is the position of the particle. Where does the particle want to be for a given energy? Make sense? Okay. I see a lot of glazing over. Maybe that was too much. Shoved it all in there. Okay, so let's stop because maybe that's too much for the end of the day.